Our second speaker, we have Professor Rafael Gomez-Bombarelli. So Rafael is the Paul Cook Associate Professor in MIT's Department of Materials Science and Engineering, as well as co-founder and Chief Scientific Officer at Lila Sciences. He earned his undergraduate and graduate degrees in chemistry from the University of Salamanca in Spain and conducted postdoctoral research at Heriot-Watt and Harvard University under the supervision of Alan Aspiro-Guzik. Rafael's research integrates machine learning with atomistic simulations to expedite the discovery and design of novel materials for applications in energy, sustainability, and healthcare. So over to you, Rafael.
Thanks so much for having me. I'm very excited to be talking to this crowd. I'm on the opposite side of the time zones, as you would expect, being typically based in Boston, but I'm in India right now, so I am ahead of you folks rather than behind. And I want to tell you a little bit about the work we've done, a little bit about sort of how I see sort of AI for science going broadly. And I've called this the bittersweet lessons. I think the promise is obvious. I think if we're all here, it's because we believe. So it's, the promise of AI for materials is huge, right? There's all these things we could do. We can make innovations in energy and sustainability, right? From, rare earth free magnets to no cobalt in batteries, to a more flexible PV. The promises of and the need for innovation in material science is critical, right? It takes about 20 years for a material to make it to market. Once somebody has a good idea, it takes 20 years for it to be deployed at scale. And for the 2050 objectives, we can't really afford 20 years, as we cannot for many other things. And the first things that come to mind is like, yeah, AI could be doing all these things. And the first question is like, well, is AI going to be a match for an okay scientist or a super scientist that does better than the best scientist, right? And these are different, in Go, in the game of Go, it looked like super intelligence, right? But in GPT, GPT is okay, it does the job. I don't think GPT writes better than me. It writes faster, but it doesn't write better. The second question is like, we're never going to have the data that's been available for other AI wins, right? Go and chess will self-play with reinforcement learning, and it's not clear how we do self-play in science. And GPT and diffusion models for images has access to all the images in the world and all the words that were ever written, right? So that's a lot of data. We're never going to be able to be like that. And then I think this audience will have bumped into equivariance and inductive bias before. It's to be determined if inductive bias and sort of knowing the rules of the game helps. I postulate that it does. I've done a lot of simulations in my lifetime, so I believe there is sort of something to be gained by having the structure of physics and the structure of science in AI for science. But AlphaFold 3 is not equivariant, so it has sort of less physics and less priors than AlphaFold 2. So maybe this is to be determined. And then the title comes from sort of this thing called the bitter lesson, or bitter. I don't know. People don't understand me when I say bitter. Is that over the last 70 years in AI, what has worked is to make models that can ingest compute. The models that can digest the more compute and thus are more scalable are the most effective, right? In AI, we turn out wanting to turn compute into learning. And if your problem can be cast as that, it means it's solvable. And that has what's powered machine vision with CNNs that did better than handcrafted feature. This is what powered transformers, taking over other sequence-based models from ancient times. That's it's bitter because it means that being smart about inductive bias is typically less important than being smart about scaling. But it's kind of sweet because it gives us a roadmap of how the world's going to look like, right? So these plots are sort of the thing that powered the investment in generative AI, is that there are pretty well-held empirical observations that models get monotonically better with more compute, more data, or more parameters. And these are 2020 observations. So this is a year after, this paper is a year after the bitter lesson comment. And if you look at these, you can extrapolate to some degree and say, well, if I'm OpenAI, I'm going to invest $1 billion, I'm going to invest $10 billion, I'm going to invest $100 billion. It's just making these things move on this log scale of gains. We also have scaling laws in materials and in chemistry. kind of the other way around. The only materials that make it are the ones that can be scaled, right? So this is truly bitter, because all the work we do in the lab, all the experiments, all the good ideas, they only have an impact if they can be made bigger. And there is clear wins, right? In energy and sustainability, right? The world looks very different to what it did 30 years ago. 30 years ago, in both lithium-ion batteries and in solar PV. Those are two technologies that have gotten pretty much, Moore's law level better year over year on some log plot. They've continued to get better and better and better, right? Because they've been able to apply the economy of scale, but also there are places where the science could sort of be made to work to achieve cheaper and more scalable solutions. So we have kind of the mirror image scaling laws in the sciences, maybe. What's scaling well? What's exciting about scaling in AI for science? Well, generally things scale well when they live sort of in a data-rich paradigm, right? Historically, science has been conducted in a sort of data-poor paradigm, chemistry and materials, maybe astronomy not so much, with so many stars in the sky. I'm not an expert, but definitely chemistry has typically been sort of a place where one postulates hundreds or thousands of ideas of, I could use this ligand, I could run at this temperature, right? The phase space of options is relatively small. The phase space of the flow of data is relatively small. One does, an experiment a week. It's been a long time since I was in organic chemistry lab. I think 2 reactions a day was already crunching, right? And then we use our own cognition to analyze the data that's coming back, right? Because at this low data regime, our mind is very good at finding patterns sort of in 2, 3, 4 points. Our minds and our intellectual understanding of the sciences allows us to use little information, sort of very compact manifolds of reasoning. AI works better in the other pipe, in a pipe where there's much more options, like of all the peptides in the world, which one am I going to make today? Right? Those are astronomical search spaces that are kind of mind-boggling, like chess or Go, where there's just too many options. We ideally couple these to richer pipes to make more data. And this data, in computation, this is easy, right? We've seen this already happen, right? In the days of, materials project, and now the data sets coming out of Meta, 1 million points, then became 10 million points, then became 100 million points. In experiments, it's more complicated, but we've seen some high throughput experiments, including in the previous talk. And these larger data sets are now not analyzed by AI, they're analyzed by sort of active learning loops that close and again. So what are things that are looking like they scale and they behave nicely? I would say structural property relationships, what we used to be called QSAR, going from the structure of something to its performance or to labels, it works. There are representation learning tools over atoms that just work. And once one is at that sort of 1,000 or more data points, it's easy to supersede traditional approaches. And the more data you get, the better these models perform, right? So it has the scaling behavior that I was talking about, right? These things become better with more data in sort of a monotonic way. Things that work, and this goes back, a few minutes. Active learning. I think once you know what the design space of something is in 2, 3, 4 variables, and it's about finding the right combination of knobs on a predetermined set of variables with some measurable success. It's like, yeah, this is how good looks like. Like there's a number that says goodness. The AI works. Like design of experiments kind of worked, right? Like people were already in the 70s doing design of experiments to almost nail this. This is like a design of experiments on steroids, right? That just learns online and keeps getting better with every data point. And this has typically worked. There are examples. I've got this sort of method reference. This was molecular ligands in Nature in 2021. This is choosing the level of doping for these Nasicon lithium-ion conductors. So, a molecule, a material, and a formulation. These folks are doing electrolyte formulations with robots. I have more on that if you have time. More things that work. Synthesis planning, retrosynthesis, that works, right? I think it's been almost a decade since, a little bit less, since this paper from Martin Segler. Connor Coley has been sort of at it big time from MIT. He had a Nature paper recently on sort of arrow pushing with the ML models. Because the chemists have been so disciplined at recording how reactions happen, and there is this very well-defined notation of reactant dash product with the reagents at the top and conditions at the bottom of the arrow. There are databases with millions of reactions that allow training models. It can be transformers based on smiles or slightly less sort of unscientific choices, or not unscientific, but slightly more inductive bias choices. But this works, right? And there are companies that offer retrosynthesis as a service, and AI retrosynthesis outcompetes other offerings out there, and it outcompetes most humans. And the same is true for materials. Materials is trickier because there's no beautiful database for material reaction, right? Materials are a mess. The reactions and the chemistry that makes materials is written out in English in papers using different words, using different sort of syntaxes, using different synonyms and different degrees of specificity. So it becomes more complicated. And this mostly took off after some heroic work pre-LLMs, after LLMs, right? Because now you can put a paper into ChatGPT and it will process the tables, it will process the paragraphs and just extract the information. So suddenly we're back on having access to thousands and thousands of synthesis recipes for materials, and then we can train models, either predictive or generative, that tell us how to do material synthesis. And this was behind the Nature paper out of Cedar Lab in 2023. We've been doing it for zeolites for a long time, and this typically works. A little bit more recent, these papers are sort of late 2023 and after. We can use LLMs, we can use AI as sort of a decision maker in workflows, decide whether to pipe things one way or another, things that we used to think require maybe a master's degree of knowing I'm going to do this and then I'm going to do that. Those things are kind of being superseded by agents that within some small decision space of tool calling and actions, they can, based on text prompts, go take action, right? And the actions are maybe find a paper, digest the paper, grab some numbers from the paper, put them into a different tool, a simulator, maybe grab some out of the simulator and even call a lab, right? The calling a lab part is, I think, happening right now. I don't think it's settled science, but the ability of agents to orchestrate, that's absolutely a given, right? So these are examples. This is from Gabe Gomez a couple of years back. This is from Aspuro Gutsik doing agents for simulations, which is a very clear choice, etc. More things that work. Generative AI works in general. It's been sort of getting better and better for molecules for over a decade. The key question that remains is whether we have enough labels to do conditional generation. So we can definitely generate molecules. Can we generate molecules that have the right properties? And that comes more from the properties than from the generators. The generators, if you give them an easy property or a property with for which labels are easy to get, you can get conditional generation. And then the synthesis, right? This kind of works better if coupled to the type of generative of the synthetic models I was talking about earlier. Proteins, well, I think the science is clear on that, right? After a Nobel Prize for AlphaFold last year in chemistry, protein design seems to be very, very well settled, right? There is a couple of Nature papers every year, and companies that have raised hundreds of millions. Xaira out of Baker Lab literally raised $1 billion A series for protein design. So this is definitely working to the point that the market has completely absorbed it. And then materials is work in progress, but it's happening. We have diffusion models that will move atoms around and make stable, realistic structures. And the challenge now is a little bit like the molecules, label them, get them made. And my last but not least, because this is sort of very close to the things we do in my lab, is simulations. I mean, simulations have all the nice features for AI, right? Data can be generated at scale, right? Data is a commodity. If you need more simulations, you get more computers on the cloud, or you ask the government for more computer time. They typically have a lot less noise and a lot less metadata, but they have essentially no metadata because the metadata is the input file that you wrote. So all the data that's relevant is captured in the input file. That's what how a simulator works, right? You need to give a fully determined input, meaning that there is really no leaky metadata as there is with lab experiments, right? Was somebody smoking outside the window in my lab, right? Like, did I leave it open? Did I leave the window open or closed? There is like infinite degrees of freedom that are not tracked, but in a simulation, everything's tracked. So it makes for very structured, scalable data. and there is lots of things to be done. So, from ML potentials that are completely settled now, and, they will continue to get better, but they're around, they're here to stay, they're not a fad, they're extremely useful, and I think they're sort of taking over many, many tasks that we would have done with DFT, or we wouldn't have been able to do at all. And then there's fancier things, and I'll spend a little bit more time on sort of cooler things for a minute. This is from Frank Noyes' group out of Microsoft in Science this year, sampling not static structures like AlphaFold does, but dynamic structures in proportion to their likelihood, right? So the same reason we do molecular dynamics for, it turns out you can just escape with generative models. So like I said, these things are settled, they scale well, they behave well. And something that I find particularly appealing about using AI and simulations together is this idea that differentiable programming languages allow us to do differentiation of anything, anywhere, all at once, meaning that we can sort of commingle optimization and simulation in sort of, if something can be expressed as a loss, it can be learned. And that opens, and the auto-differentiable codes allows to, take gradients of that loss and just make it smaller. So there's lots of opportunities, and this is something we've played around in the group for a while. We've been in ML potential space. This is sort of one neat example where we found that this was AIMD simulation. So these orange points were people looking at the diffusivity of ion in this material, of lithium ion in this LGBS material, at full price DFT. And they were able to go up to 600 Kelvin, just because that's too slow. But the material is not stable at that temperature, right? So this was sort of pure speculation. And then the experimentalist doing NMR could measure the same thing and go all the way to 450 C, but not higher because the material decomposes, right? So there was this sort of discrepancy between what theory said and what experiments said. And it turns out we did ML potentials like many other people. We trained a custom one. This was 2022. Foundational ones weren't effective. We did 40 nanoseconds worth of MLIP simulation, and we found there is a phase transition in between. Everybody was right. These simulations were very accurate. They were just for a phase that is not the phase that exists down here, because the lithium, one of the dimensions in XYZ, one of them, the Z, gets shut down. We've done ML potentials for the excited state, and this is something we continue to be very excited about. We have ground state energies and forces. We might as well get excited state energies and forces and do dynamics in the excited state. And if these dynamics were expensive, when you have to pay ground state DFT price, the dynamics that allow you to look into photo switches are extra expensive, right? Because you don't just pay DFT price, you need to pay TDDFT or some excited state DFT or some excited state method price. So if this was worth it, this is extra worth it. There is some subtlety around how ML models handle the conical intersection, because this is essentially discontinuity in the potential surface. So we had to be a little bit smart about, or Simon was, I wasn't, but the student Simon was smart about how to handle the crossings in ML potentials through essentially throwing the diabatization into the neural network. So the neural network is trained on smooth states, but it produces the output of adiabatic sharp states. This keeps going. We've done coarse graining. You can imagine how all the pieces of coarse graining are actually machine learnable. Learning which atoms belong to which bead, that's can be cast in terms of information, maybe. Which potential the beads are being are acted upon, right? What are the forces that act between beads? And Cecilia Clementi has done a lot of this for proteins. Some of the work has been concurrent with us. In some things we've done more sort of materials applications. And then back mapping, the recovering all atom structures from beads, well, that's exactly a generative task where you need to recover a statistical distribution of states from noise, right? Because the information during coarse graining was all lost. And then this example to the left is from, it just got into Nature Machine Intelligence a couple of weeks back, using diffusion models to leapfrog molecular dynamics. So rather than run full price molecular dynamics, have an MD model that predicts what the future will look like in 25 picoseconds, right? So it's 25,000 times faster in terms of step size than than doing ML potentials, than doing simulations. If you're comparing this with a classical potential, it might be expensive, but if you're comparing it with doing ML potentials, it's exactly the same price, right? Because the architecture of this diffusion model is equivalent to an ML potential. So this could sort of be 25,000-fold gains on looking into dynamics. Yeah, it keeps going from these are fairly recent stuff. This is doing derivatives over things like uncertainty, right? We have access to all these derivatives, so we can do derivative of uncertainty to do active learning and go find regions where our models need help. We can do statistical mechanic approaches at tasks that used to be too expensive, like surface reconstruction, right? The potentials are good enough for surface reconstruction, and they're cheap enough for Markov chain Monte Carlo methods, on grand canonical Monte Carlo methods, that can figure out de novo how a surface reconstructs, right? So we can construct surface phase diagrams and their electrical and chemical potential of complex materials, right? So this is an example. This is strontium titanium oxide in the gas phase against the chemical potential of oxygen. This is a surface phase diagram for lanthanum manganese oxide, a perovskite, that could be a useful catalyst, but it's not particularly stable in high pH. And then you can see sort of what the surface termination is, right? So this area is manganese oxide with 1 out of 4 absorbed hydroxides, etc., etc. And this is my last example. So for sort of handshaking simulations and AI is alchemical methods brought to machine learning potentials. It turns out ML potentials are implicitly differentiable with respect to alloying. One just needs to make a ghost atom, have an atom that has sort of a superposition of representations that is at the same time the two members of the alloy or the n members of the alloy. And by just modifying the way we do message passing between ML potentials, inside the ML potential, we can get the behavior of disordered alloys for free. So we can go and be rid of special quasi-random structures. No more SQSs. We can recover the right energies for disordered systems with much smaller supercells, representing chemical disorder as alchemical doping of various elements in the lattice. This is, for instance, for optimization, finding what is by just gradient descent, finding what is the ideal alloy in this aluminum scandium yttrium nitride, right? So it's disordered over scandium yttrium, and we're doping how much of them we need to hit a certain lattice match. So we can do sort of design problems and free energy approaches on alchemical atoms. Okay, so all those things are sort of very promising. I think it's the evidence is, in my opinion, definitely favorable to all those things. What is slightly less sort of a slam dunk today? Well, there are some things that I don't think are necessarily solved problems yet. The first one is, I think, it's going to stay. AI doesn't decide what's important, right? We decide what's important. Of all the problems I could take in the world, of all the things I could spend my money on, of all the students I could hire, right? Of all the, these are values decisions, right? They need to represent that they're really not objective scientific decisions. They're value-based decisions. And AI doesn't right now have values of its own, hopefully, and it doesn't necessarily reflect ours. So it's not, it cannot make value judgments. The interface of scientists with AI is also not very clear. One part of it, asking ChatGPT to read papers for you or to write cover letters for you, that's settled. But the other part of having AI tell scientists what to do, that's people generally don't like to be told what to do. I think scientists less than other people, and less so by computers, right? We want in a place where we tell the computer what to do, and it's less exciting to be in a place where your work depends on receiving input from a computer. Right? We want to feel that we're creating value. We want to feel that we're being smart and making our choices right. And the interface of AI and scientists is not a solved problem in that sense, especially for like enabling AI designs, right? AI could invent all these things, but they need to be made by people. That's not trivial. Because AI doesn't make anything, right? And you could tell me, well, if you have an AI programmable laboratory that makes stuff, then yes. But the gatekeeper there is having a programmable laboratory, right? Self-driving labs are composed of two things: the AI that drives and the actual physical connections and pipes and robots and actuators and heaters and programmable laboratory elements that are not trivial. They take a lot of work, take a lot of time, they cost a lot of money. And I could drive a programmable laboratory without an AI. So that the laboratory is programmable doesn't make it sort of an automated AI lab. So this interface is being worked upon. I mean, we've seen evidence in the last talk, and I will show a bunch more, but it's not a solved problem either. AI doesn't know when it's doing wrong. I mean, I'm sure you experienced this. I experienced this recently when ChatGPT calculated that storing 100 terabytes of data was going to cost us $10 million per year, because he got confused about how many terabytes there are in a petabyte. They kind of confused terabytes and petabytes, which is a factor of 1,000, right? You would fail a first-year grad student or a first-year undergrad. Right? You show up to a physics class, you confuse peta with tera, and you just fail the class, right? Because you need to know what you're talking about. ML potentials can do the same thing, right? This applies to all types of models. Generative models won't know when they're giving you sort of rubbish candidates that can't really be made or they don't really fit the label. ML potentials won't tell you when they are sort of giving you the wrong forces or the wrong energy. So generally, AI is not good at self-diagnosis, and it's not good at understanding the depth of all the things, right? We have a lot more context, we have a lot more awareness, and AI models trained to do one thing, do that one thing. So synthesis models won't really know about properties. Generative models won't know about synthesis unless they're trained together. And this keeps going and going, right? There is no, right now, good understanding of the implications of actions and decisions. So what sort of worked, in my opinion, for closing the loop and bringing all the pieces together? Generally, being in a combinatorial space where there is just many options, being able to help with theory is typically helpful, in my opinion, like create some prior knowledge, training data that's sort of cheap. This is very filling, but maybe not very nutritious. That allows to get the sort of the machine going. Read the papers like students would, right? Like when we all started our degrees, we were told, well, just go read this and that, and then you go to the lab. Well, the same applies to AI, right? We shouldn't be starting anything from scratch. Everything should be starting from pre-read, and especially in the days of LLMs, where they can find the papers themselves, they can read the papers themselves. We should definitely be starting warm everywhere. There might be some ML innovations, and then we need to be able to cycle, right? Zero shot, it's kind of doesn't work yet. I think expecting a foundational ML models to solve open scientific questions on their own in zero shot is unlikely. There are examples, and that's, I think, was part of the beauty of AlphaFold, that it kind of didn't need a lot of active learning, but typically we do need to validate hypotheses, right? We need a mechanism. That's what science is about, right? Science is not about making hypotheses, about validating them or falsifying them. So we need some mechanism for that, and it needs to be in a quantity and speed of data that is compatible with AI. Things that take a year are probably not the best for active learning, right? It's going to take such a long time to cycle. It doesn't really create a lot of value. So I have some examples. I don't think I'm going to have time for everything, so I'll walk you quickly through one or two, and to give you a taste of how these things have come together. One is in a class of material called zeolites, the nanoporous materials that came up a minute ago. They're a nice playground for AI, right? Because they're highly combinatorial. They're also important, right? There is a multi-billion-dollar business riding on them for cracking in oil and gas and for diesel emission control. So they're important class of materials. There's appetite to make more. We have about 12 in the market. There's about 250 that have been made in some composition, and there's like 1 million of possible ones whose energies and properties seem okay. They're just not makeable. And these materials, like I said, are nanoporous aluminosilicates, and whose porosity influences their applications. They're made by putting inorganic precursors in an autoclave and cooking for some period of time at a certain temperature, and that goes from a starting material to an amorphous gel to a crystal over the course of maybe a week. And the secret ingredient for zeolites is that they're typically made, or they're oftentimes made, using templating molecules. These templating molecules fit the pore so tightly that within the amorphous gel can lean the kinetics of crystallization one way, or they can tilt, sorry, the kinetics of crystallization one way or the other by changing the energy landscape of certain material versus another, right? But by creating this sort of local driving force for a certain pore, they can infer the formation, they can force the formation of one material or another. So in this example, it turns out this is something you can calculate, the affinity of a certain substrate to a certain pore. People had done that in the past, right? You can see that this from this figure that this paper is pretty old. People have done this in the past. They just hadn't done it at scale. So they typically fail because there was another zeolite that was more affine to the molecule than the one you thought, right? So being a strong binder was a necessary condition, but it wasn't sufficient. In order to be effective, one had to have selective templates. So here we took a brute force approach at selectivity. We calculated how all known OSDA molecules, over 1,000 from literature, fit the 250 frameworks. And with this table, validated by literature that Elsa, Professor Olivetti extracted before LLMs, we were able to make a portal to visualize the calculations and data mine, which molecules are selective for which zeolites. And we've made all sorts of zeolites. We've made many intergrowths. An intergrowth is a single crystal that has sort of subdomains of two different materials. This is an intergrowth between three materials. This is putting some of these intergrowths to work in a catalytic reduction of nitrogen oxides, and without aging, all the materials that we made are the same. But with aging, the cheaper material was the least performant. This more expensive AEI was better performant, and these two integrals have domains of AEI and domains of chabazite that are made with a cheaper template, perform as sort of linear interpolations of their endpoints. And these two new materials, they haven't been made before, and there's sort of an example of getting something done all the way into patent filing from a purely computational screening beginning. This is an example of literature work for the inorganic conditions, right? I just said that's a molecule. The molecule we can do with physics, pretty okay. But then there is the time, the concentration, the temperature, which precursors to use, and what relative ratios of elements. So all those things can be learned from the literature. There is about 70,000 zeolite papers in the literature, and about 10,000 zeolite recipes that have been extracted from the literature. And with 10,000 points, you can train a pretty strong ML model that predicts how to make a zeolite. Given a zeolite, what are the ingredients? What are the things that make that zeolite form? And then, because there had to be so machine learning, there wasn't a lot of machine learning in the computational work. I mentioned we did all known molecules and feed them into all known zeolites. But what we want to do is to invent new molecules. So in this case, we didn't do generative AI. We just went to the catalogs, downloaded all the molecules that make sense as precursors. Most of the templates for zeolites are quaternary ammonium salts, and you can make quaternary ammonium salts with amine and electrophilic molecules with leaving groups, right? Halides. So we got all the amines, all the halides, we put them all together. That's 2 million molecules. We took our model that we had trained on known molecules, and we put it against this 500 million matrix, right? We went to a matrix that has 2 million molecules, 250 zeolites, and we just filled that matrix to the best of our ability, meaning that now we know pretty much where every molecule fits and where every molecule would be selective for which zeolite. So we haven't invented any new zeolites yet, but we invented a bunch of new molecules that sort of do cool tricks, such as pushing zeolite composition to the highest aluminum loading, or pushing zeolite composition to the lowest aluminum loading. So what I'm going to do, I have another sort of narrative that is very similar around battery electrolytes. If anybody's super excited about battery electrolytes, I can send you 2 or 3 references. The very similar game plan, right? We can do stuff in the lab with formulation works well in the lab, right? It's not easy to simulate formulation, but it's easy to mix in the lab with a robot. So there's a little bit of lab wins through active learning of formulations, and there's a little bit of chemical space wins with molecular dynamics. And in both cases, we found that we can beat the literature either keeping a model blind to the literature, doing closed loop experimentation in the lab, or doing high throughput molecular dynamics that can accurately, this is the relationship between MD ionic conductivities and experimental ionic conductivities. And with this, we feel we're equipped to go figure out what's the highest conductive ionic conductivity polymer we can find. I think, you know, we're in the right space. I would congratulate everybody because it's sort of the years of AI for science. There's a lot to be done, right? We need to take this into the market. We need to show that we can make materials at scale. But you can see, you know, I postulate that the small molecule drug design is taking a breather right now after a big push in the 2018 to 21 company creation. So I think we're waiting to see where the small molecule drugs are going. Protein design, AlphaFold has been an unmitigated success for now. And then this idea of how do we make actual things that perform at scale is exciting for me and for many companies out there. And just a quick shout out that since June 1st, I'm full-time at Lila Sciences, trying to bring all these things together with sort of a stellar team that you're probably going to know these guys, and many other people trying to make a scientific super intelligent a thing that goes beyond the research institutions and becomes sort of a little bit more tangible. So I will thank the team. Thank you so much, folks, for your attention.